We present goal-aware prediction, learning to model what matters. Deep model-based reinforcement learning has shown promise in a number of settings, ranging from challenging robotic control to learning directly from pixels. These methods exhibit numerous favorable properties, including sample efficiency, stability, and interpretability. However, scaling these methods to diverse visual scenes poses numerous challenges, the primary of which is underfitting, even with very large models. In these settings, the learned model cannot perfectly model the scene. As a result, learning algorithms must balance how best to learn their model to achieve good performance on downstream tasks. Specifically, in many cases, there exists an objective mismatch, where better performance fitting the model does not directly translate to better performance using the model with planning in a downstream task. We begin by investigating the relationship between model error and task performance. In this setting, we will consider the following assumptions, specifically, that we're using a simple planner which evaluates action sequences over a learned model and selects the lowest cost action. Each action sequence will have a true cost in the environment as well as an estimated cost under the model, which will be affected by model error. Without loss of generalities, let the trajectories be ranked as shown. That is, under the true cost, the planner will select action sequence 1 as the best action. We aim to understand under what conditions does the planner's behavior remain epsilon optimal. That is, the chosen action sequence has true cost within epsilon of the best true cost when planning under the learned model and estimated cost. We showed that if the prediction error on the best trajectory is bounded by epsilon, and the prediction error on the suboptimal trajectories are bounded by their distance to the optimal trajectory, then the planner will remain epsilon optimal. Note that the allowable error bound scales with how far from optimal the action sequence is. The key takeaway being that to maintain task performance, the greater the true cost of a trajectory, the more prediction error we can afford. Motivated by this analysis, we asked the question, how might we encourage a learned model to be more accurate on the best trajectory? We propose conditioning the model on the goal and learning in a way such that it only captures the necessary information for that goal. We assume the self-supervised setting where we do not have access to any task-specific rewards at train time, and at test time, the aim is to plan using the learned model to reach unseen goals. To this end, we propose goal-aware prediction, or GAP. Unlike a normal latent dynamics model, which encodes the current observation, GAP encodes both the current observation and goal into a latent space. GAP then reconstructs the difference between the current state and goal from the latent encoding instead of the full observation. As a result, the latent space does not need to capture any information about the task irrelevant object, such as the green block in this case. Then forward dynamics are learned in this latent space. Critically, since we're in the self-supervised setting, we don't have access to true goals. Instead, we leverage hindsight relabeling to acquire goal-reaching trajectories. In our experiments, we examined 3 primary questions. First, how does GAP redistribute model prediction error? Second, how does using GAP lead to better downstream performance on control tasks? And lastly, does GAP scale to real cluttered visual scenes? In our experiments, we test on a suite of simulated robot manipulation tasks, as well as a real robot manipulation dataset. First, we examine how GAP redistributes model error in the simulated domain. We do so by sampling 1,000 random trajectories for an unseen task and ranking them by their true task cost. We then measure the model prediction error over the prediction horizon, average across the top k trajectories, where smaller values of k indicate better trajectories. We compare GAP in blue to the standard latent dynamics model in orange, and observe that while over all 1,000 trajectories, the performance is roughly the same, while looking at better and better subsets of trajectories, GAP has relatively lower prediction error. This suggests that GAP is more accurate on the best trajectories. We observe this qualitatively as well, where GAP more effectively models the target object in a good trajectory, seen in the middle, and does not model task-irrelevant objects at all, as seen in the predictions on the bad trajectory on the bottom. Next, we examine if GAP improves downstream task performance on unseen tasks in a simulated manipulation domain, testing on the block or door manipulation task shown in the top right. We report the task success rate when used with sampling-based planning. We find that compared to the standard latent dynamics model, as well as the self-supervised model FRL technique rig, and a latent dynamics model learned with the inverse model objective, GAP is the strongest performing method. Lastly, we study if GAP can be applied to challenging real-world data sets and complex visual scenes. To do so, we combine GAP with an action condition SVG video prediction model, where now, when combined with GAP, the SVG is conditioned on the goal and predicts the sequence of goal state residuals. We compared these approaches in their test prediction error on goal-reaching trajectories on both the RoboNet and Bear robot dataset. and find that gap and gap without residual prediction outperforms Nair and SVG. By conditioning on the reach goal, gap is able to focus its capacity on modeling the components of the scene which are relevant to the goal, as seen in the video on the bottom right. The key takeaways are, for model-based planning, model error on the best trajectories is most critical for task performance. Gap helps redistribute model error to be more accurate on task-relevant states. And using gap leads to improved downstream task performance. Thank you.